Alright, in this video, we study how we can apply the kernel method to nonlinear classification problems. Suppose we have the set D of two-dimensional points, which is partitioned into two parts, D plus and D minus, which are mutually exclusive or disjoint. And each of these points is labeled by lambda j. When xj, yj belongs to D plus, then the label is positive 1. Otherwise, the label is negative 1. The classification problem is to find some function, in this case from two-dimensional plane to a real number, such that those points that gives positive value of this function is a superset of D plus, and those points that give a negative value of this function is a superset of D minus. Now, let's consider an example. Suppose we have this set of points, and these are the points in the subset D minus, and these are the points in the subset D plus. In this case, we can just draw a straight line to separate these two subsets. In this case, this line will be the classifier. F of xy will be something like ax plus by plus c, where a, b, c are just some real constants. Finding this straight line is not a difficult problem, and we can use a standard technique of linear discriminant analysis. And in this case, the set D is called linearly separable. Next, consider this example where the points in D minus here, it's surrounded by the points in D plus. In this case, obviously, we cannot separate these two sets by any straight lines. So we need something else that may be, for example, a circle or ellipse like this. And of course, this cannot be expressed as a linear function, and we need some nonlinear function, such as f of x, y, a plus bx, cy, plus dx squared plus ey squared. Now let's see how the kernel method fits into this problem. First, consider a function which we call the feature function from the two-dimensional plane to a five-dimensional space, which is defined as, so point xy is transformed into a vector 1, x, y, x squared, and y squared, which is in the five-dimensional space. And then we define a kernel function, k. So this takes 2 points in two-dimensional space, let's say xy and zw. And this kernel function is defined as the inner product in the five-dimensional space. So phi of xy times phi of zw in five-dimensional space. This is equal to 1 plus zx plus wy plus z squared x squared plus w squared y squared. And if we have a vector v, a, b, c, d, e in the five-dimensional space, then the inner product between v and phi of xy is a plus bx plus cy plus dx squared plus ey squared. So the present nonlinear classification problem may be solved if we can find a vector v such that the image of d plus by phi is a subset of this set, x in the five-dimensional space, where the inner product between v and x is positive, And the image of d minus by phi is a subset of this set. The inner product between v and x in the 5-dimensional space is negative. So we can write the classifier f of xy as the inner product between v and phi of xy in the 5-dimensional space. Later, we will see such v can be expressed as a linear combination Cj of phi of xj, yj, where each xj, yj is an element of the dataset. So if we substitute this v into this, we have f of xy is equal to sum j from 1 to n cj of inner product phi xj, yj, and phi of xy. And of course, this is the kernel function, so we have the kernel xy and xj, yj. And this may be written as a linear combination of the parameterized version of the kernel functions, parameterized by the data points xj, yj of x, y. So the function here, this classifier function, is written as, just like in the representer theorem, we have cj, k, xj, yj, like this. Now let's prove the following theorem that says the classification of a given dataset is always possible under a certain condition. Let D be a dataset consisting of x1, x2, up to xn, which is a subset of some set x. And Hk be a reproducing kernel Hilbert space. And let phi be a map from x to hk. And consider this map as follows. So let x be an element of x, and then phi of x is the reproducing kernel parameterized by the point x. This implies that the kernel function at x and y is equal to the inner product between kx and ky of hk, which is equal to phi of x and phi of y in the Hilbert space. Anyway, if these vectors phi of x1, phi of x2, and so on up to phi of xn, if these vectors are linearly independent, then for any partition of D, that is D plus union D minus, where D plus and D minus are disjoint, we have phi of D plus and phi of D minus. These are linearly separable. Okay, let's prove this. First of all, what this statement means is the following. There exists some element v in the Hilbert space such that phi of d plus is a subset of this set if an element of hk and the inner product between v and f is positive, and phi of d minus is a subset of this set. Inner product between v and f is negative. So our goal is to find such an element v in the Hilbert space. And for that, we first define a subspace W, which is spanned by the vectors phi of xj. So it's a subspace consisting of all the vectors that can be expressed as linear combinations of these vectors phi of xj, j from 1 to n, where each cj is a real number. J runs from 1 to up to n. And next, for each j from 1 to up to n, we define wj, which is the intersection between w and another subspace that is orthogonal to all other vectors than phi of xj. So that is f in hk, and the inner product between f and phi of xi is 0 if I is not equal to j. And by this definition, we know that the dimension of wj is 1. And also, there exists some element, let's call it lowercase wj, in W, such that the entire wj can be expressed as a scalar multiplication of this lowercase wj. And of course, we have the inner product between this lowercase w and phi of xj being non-zero. So we can normalize this vector and so define vj as double j divided by this inner product, double j times phi of xj. Then we can write the inner product between vj and phi of xi as Kronecker's delta ij. So if I and j are equal, then this is 1. And if I and j are not equal, then this inner product is 0. Next, let us define the labels of each point. Define lambda j as +1 if xj belongs to d plus, or -1 if xj belongs to d minus. And using these labels, we define the vector v as the sum of j from 1 to n and lambda j times vj. By construction, this vector v is an element of W. And the inner product between v and phi of xi is this. Sum of lambda j times vj times phi of xi. But this is Kronecker's delta, so the result is lambda I, which is +1 if xi belongs to d plus, or -1 if xi belongs to d minus. So this means the hyperplane v times f k equal to 0. So this defines an hyperplane where f is the variable in the Hilbert space. So this linearly separates the sets phi of d plus and phi of d minus. So this v, or this v, is the v we were looking for, and we are done. So after we transform the original data in the set X into the Hilbert space HK through this feature map phi, then the problem is now linearly separable. So we can have the classifier as a hyperplane like this. But in the original space, it is still a nonlinear function. So let's see how it looks. First of all, if you trace back how we defined the vector v, it can be actually represented as a linear combination of phi of xj's. And if we have a point x in the space x and apply this hyperplane, we have v times phi of x equal to 0. And the left-hand side is this. If we use this linear combination, it becomes j from 1 to n, cj, and phi of xj times phi of x. And we define the kernel function as this one. So this is equal to kernel function of x and xj. And if we use the parameterized form of the kernel function, kxj of x. So if we define the classifier of points f of x as this function, then the function f itself can be written as a linear combination of the parameterized kernel functions. Here, be careful that this f has nothing to do with this f here, okay? They are completely different stuff. So in the actual classification problem, for any x in the space x, if f of x is positive, then we classify x as belonging to D+, and if f of x is negative, then we classify the point x as belonging to D-. In this video, we implicitly assume that we have some explicit form of this feature function phi from the space x to the Hilbert space. However, the real power of the kernel method is that we don't really need to know the explicit form of the feature function. We only need the kernel function, which is a lot easier to calculate. And hopefully such a use case I will explain in a later video. Okay, that's all for this video. See you later. Bye. Thanks for watching. If you like this video, please hit the like button and subscribe to this channel. See you next time. Bye.